Hi, this is Dan Bullard, retired electronics engineer, sitting on the front of my house again. It's Saturday, so hopefully we're not going to have too many interruptions. Okay, I want to start another mini-series like I did before with the Nextest DSP class. This is going to be the Nextest MSPC class. Nextest Mixed Signal Pin Card. And I'm doing this because I wrote this course years ago when I worked for Nextest. And my boss recently died, Rick Carmichael. He recently died, and I went through Teradyne's webpage, and they don't even mention the Nextest, so they probably don't care about this stuff at all. But I'm going to give it a shot. So the Nextest they're actually derived from Megatest. Megatest made the biggest tester I ever heard of, and they tested a lot of stuff. And they finally got into doing memory, and the company was sold to Teradyne. The founders got out of there and formed a new company called Nextest, and they started just testing flash memory. And they made a Maverick, and that was a 64-pin tester, and they made the next thing, which was an ST, and then SST, and then they finally made a GT, which was, I think, 512 pins. It was huge. And then Rick Carmichael joined up, and he said, let's put mixed signal in this. And they did. So they added mixed signal. My buddy Mike Furlan did it, along with Jim St. Jean and David Reynolds from Protest. And they tried to get me in there. They tried recruiting me several times and finally talked me into it. So I went to work for them, and it was great. It really was great. I worked there for quite a few years, made a shitload of money. They even gave me a lot of options, a lot of stock options. So I walked out of there with well over $100,000 in stock. So it was great. But the problem was they're making me travel like crazy, so I had to get out of there. So I finally did. So here is the Nextest MSPC Mixed Signal Pin Card training course. I'm going to do the first part now, and I'm going to try to do some number segments of it over time. Hopefully it doesn't take too many, probably 5 or 6, hopefully not too many. Okay, we'll start off with day one stuff and an overview of Lightning, configuration options, MSPC overview, that's a mixed signal pin card overview, just one card. We're not going to get through all of that today. In other episodes, we're going to talk about the clock generation, which is what makes it coherent. That was done by Jim St. Jean and David Reynolds. And that's a huge thing. The AWI and the ACI. Then we'll talk about how the instruments work. The instruments are really cool, and I had something to do with it. When I went on board, they had a really good idea of what they were going to develop. But I got in there a little bit early, so I was able to get some of my ideas injected into it. So we get into the PMU, bias source, DPS, that's a device power supply, modulator, and DCI usage. Okay, what is Lightning? Mavic 2 tester with 1 or 2 MSPC cards per 64-pin slice. So 16 pins of analog replaces 16 pins of digital. So you can either have 48 pins of digital and 16 pins of analog, or 32 pins of digital and 32 pins of analog. So here it is. This is what it looks like, and you've seen pictures of it, I swear. You've seen pictures of it when I was doing a demo with me and my tux. That's a Lightning. And it's a box with 5 cards in it. And it started out with an APG card, then a PE card for pins 1 through 16, a PE card for pins 17 to 32, PE card as pin electronics for pins 33 through 48. We pull out the pin card that would have been there for pins 49 to 64, and we replace it with an MSPC card. That's the mixed signal pin card. So that occupies the last 16 pins in that Maverick, and that's a Lightning. Now the other way you can go, and nobody ever did this, is you could have 32 pins of digital and 32 pins of analog. So you have an APG, algorithmic pattern generator. And then you have a PE card for pins 1 through 16, PE card for pins 17 through 32, and 2 mixed signal pin cards. Then you can do an ST, which is 128 pins. So 112 pins of digital and 16 analog pins. And you can go up to 64 digital pins and 64 analog pins. That's a lot. You could have an SST, which is 256 pins. So 240 pins of digital and 16 analog pins, and up to 128 digital pins and 128 analog pins. And you go to the GT, which is 512 pins. You can have 496 digital pins and 16 analog pins, or up to 256 digital pins and 256 analog pins. Maxim did, I think, the SST. So they actually had a pretty beefy system. Those testers came out to close to $1 million a pop. And I sold them. I'm the one who sold them. And I did the apps to show that it worked. And Don Greer bought them. And next thing you know, they were testing parts and I bailed. Okay, what is an MSPC? A mixed signal pin card provides 14-bit source and capture. That's the AWI and the ACI, plus one 16-bit VI, that's a voltage or current force unit, 4 analog bias supplies, that's 16 bits, 2 DPSs, device power supplies, a differential voltmeter, and then a DC and HF matrix. The mixed signal pin card provides the infrastructure for mixed signal modules. Up to 6 modules can be installed. Modules can be single or double size. The standard modules address common test requirements. Specialty modules address specific custom test requirements. Now, we had that in the case of when I was at Credence. We actually had LSI. You've probably heard of them, LSI, which stands for Large Scale Integration. But LSI was a company that was in California, and they also had a place up here in Gresham, Oregon. And I did some work for them. They need to do IDDQ, and I don't want to get into the whole thing with IDDQ. IDDQ is really cool. You know, each chip has millions of transistors, and can you verify that each and every transistor works perfectly? You can if you use IDDQ. And so LSI wanted to do IDDQ, and I worked on the VI for the Credence systems, but the problem was the VI wasn't capable of doing IDDQ. So we had to get a company come in to do a card for the Credence that would do an IDDQ. So they came in and they built a card, and I was leaving just as that started happening. So the salesman called me up and said, "Dan, I can't believe you're leaving. What's going to happen to this project?" Well, it's just we're going to have to live without it. But when I went to Nextest, I understood IDDQ really well, so I made specific requirements for the MSPC to handle IDDQ. Okay, here's a mixed signal pin card layout. It looked kind of like this. It had a lot of stuff on it. It had a clock generator card that was built by Protest. That's Dave Reynolds and Jim St. Jean back in, they were back in New Hampshire. So that's a clock generator, and we're going to talk about that in another episode. Below that is some regulators and a DC-DC converter. Now, they built this unit, this mixed signal pin card, so it can float relative to the rest of the tester, because in a true mixed signal tester, analog pins are different. They float at a different ground level than the digital pins. So the analog and digital pins grounds can be connected together right at the socket. So analog ground and digital ground are two separate things, and then they're connected together right on the load board, right at the device. Analog ground and digital ground are supposed to remain totally separate all the way up to the load board right under the device. And their analog ground and digital ground connected together. So we had a DC converter in there. Mike Furlan designed that. So it took the DC from the Mavericks power supplies. It turned it into DC that was isolated from the rest of the Maverick. So here we had a card in the Maverick cage that was floating relative to the rest of the board. So all the signals came out of this, they were all separated from the grounds in the Maverick. It was quite a unit. Now that caused problems that I'll tell you about in a minute. We also have the trigger memory, a cal module for calibrating the thing, so it had its own little cal module. It could be removed and taken off to a cal lab, and then the calibration could be done on it, so the unit would be calibrated relative to the cal module. Here are the 4 bias supplies. There are 4 bias supplies in there. There's a VI, 2 DPSs, device power supplies, control, and then above that says DAX and modulator. So the DAX for all those things and a modulator. What's the modulator? The modulator you'll see coming up, it actually allows you to do modulation on the DPSs or the bias supplies, so you can modulate the voltage going into the part, so you can do like a power supply ripple rejection test. So you can modulate the DPS, modulate the bias supplies, so you can put a sine wave on them or any other kind of wave you want. And we used to do that, I mean, way back when, back in 1990. I had to do that for the anti-lock braking system for the GM anti-lock braking units. I had to make a test for that, and I modulated the power supply for the ABS unit, because when you have a car and you do something as crucial as analog braking, you've got to make sure that if the voltage going to the battery is varying a lot, it doesn't mess with the ABS. You don't want it to slam on the brakes just because you turned on the radio or the heater, you know, or the air conditioner came on. Oh no, suddenly your brakes slam on. You don't want that. So I had to do a test for Philips for the ABS module, and that included modulating the digital supply to that ABS unit so that we could make sure it wasn't going to like blow up the car. So the modulator can do that on any of the bias supplies or on any of the DPSs. Now staying on top, we go control and the ISO bus and the computer interface. So the Maverick has a computer interface. So the Maverick runs off of a PC, and how does those digital signals get onto the board? Well, we can't just wire them directly to there because the whole thing is floating. So Mike Furlan designed a circuit using capacitors. So the digital signals that came from the PC to program all this stuff was isolated through capacitor. So it's actually capacitive coupled to all the digital in there. Now, that created a problem. Mike was brilliant, but he wasn't perfect. And so that created a problem. And so Mike ended up having to connect the ground on this board to the ground on the tester through like a 10K resistor. So it was kind of isolated, but we had to worry about the capacitors getting too far charged one way or the other. And so that took care of it. So we had like a 10K ohm impedance between the digital ground and the analog ground, which was pretty good. Okay, below all that, we have the specialty slots, the source slot, and then the buffer slot. And that covers up the DC matrix, which is on the back side. So the DC matrix is basically a bunch of relays, and that's on the back side. But in front of that is all these slots to take these modules. So these modules, and I'll show you the modules, mostly it's the AWI and the ACI, but the idea was that we could come up with other modules if someone needed some special thing to do, and we could do that. Next to that is the AC matrix. So the DC matrix has all the relays that take the VI and the bias supplies, and then we combine that with the AC matrix, and then in front of that is the ACI and the AWI. We have two matrices. We have a matrix for the AC and a matrix for the DC. Two matrix solution optimizes AC performance. The HF matrix connects mixed signal instruments to pins. It's impedance match with no stubs in the path. Stubs are a big deal. When you shoot a pulse down a line, if there are any stubs, it'll cause a reflection, and that's bad. You don't want that, so no stubs. The DC matrix connects DC instruments to the pins, and it's a Kelvin matrix. So that means there are two lines, force and sense. And so the DPSs, the bias supplies, two of the bias supplies have force and sense. Okay, here's what it looks like overall. You've got the two DPSs that do not go through the matrix. You have the VI, which is voltage force, current force. So in voltage force, generally you do current measure. In current force, generally you do voltage measure, and that's a Kelvin setup. So there's two wires coming out of there, force and sense. Then you have two bias supplies that are Kelvin. So bias source 1 and bias source 2 are Kelvin. They have a force and a sense. Bias source 3 and bias source 4 do not have force and sense. They're just a single-ended bias supply. We have a differential VDIF, so differential voltmeter, 16-bit voltmeter, and it's not like an HP 3458 or anything like that. It's a voltmeter that we build, and we measure it. We do all the stuff with the VI. It's really cool. And then below that are the two instruments that we built for this thing. Well, Applicos built them. It was the AWI and the ACI. The arbitrary waveform instrument and the analog capture instrument. Those go through the HF matrix. Anything on the DC matrix can connect to the HF matrix. And then we have 16 pins going out. So pins 49 to 64 going out to the device, to the pins, and we can force a voltage, we can measure a current, we can force a current, measure a voltage, we can send an AWI out there, we can have an ACI digitize, we can have the VI digitized, we do all kinds of stuff. The AWI and the ACI were built by Applicos, and that's how all this came about. Rick contacted lots of companies. He finally talked to Applicos. They had the instruments that we could work with, and so they built the AWI and the ACI. The AWI was a 14-bit 80 megahertz AWG, and the ACI was a 14-bit 65 megahertz ADC. Generally speaking, AWGs run faster than analog capture instruments. That's generally the case. Here's a block diagram of the AWI. It's got a clock generator coming in to a memory address counter. You've got 256K waveform memory. The memory goes to a 14-bit DAC, so that's 14 bits going into a 14-bit DAC. The output of the DAC goes to a set of filters, a 30 megahertz low pass, a 15 megahertz low pass, a tunable low pass, or you can bypass the filters. Then it goes to an amplifier. We have a 16-bit offset DAC. Let's say you got to generate a 1 volt peak-to-peak waveform with a 3 volt offset. You don't have to set it up in the memory with a 3 volt offset. You program the waveform you want in the waveform memory, and then you use the offset to give you that 3 volt offset. So now it's a 1 volt peak-to-peak waveform in that memory, and then you use 3 volt offset in the offset DAC. So that goes to an amplifier, and then coming out of it, it's a differential amplifier going to 4 drivers. So you can drive on 4 channels at once if you want to, and it's differential all the way. So the AWI spec is 14-bit 80 megahertz max AWG. It has minus 80 dB THD at 1 megahertz. Notice we're talking THD, and minus 70 dB THD at 10 megahertz. We actually had the students test this. Okay, we go from minus 0.5 volts to 5.5 volt maximum voltage. Most chips, even now, I mean, they're only going to 3 volts, but back then, most chips went up to 5 volts, and we could handle that easily. It could be single-ended or differential. And you had 15, 30 megahertz or tunable low-pass filters. And here's a picture of the AWI. Now again, this was built by Applicos. So this was a card that plugged into the mixed signal pin card, and that is the AWI. That's a complete AWG with 256K deep memory, 14 bits wide. It was a great little AWI. Okay, here's the ACI block diagram. Here's the input multiplexer. So we come in from the other pins up to 8 inputs. We only use 2 pins at a time if it's differential. If it's not differential, we only use 1 at a time. So we come into the input differential amplifiers. We can go into the upper path, which can go through, that's the LF path. We go to a tunable notch filter. The notch, if you read Bruce Tibbitt's application note on doing THD, he talks about using a tunable notch filter. You can do that. So if you want to do Bruce Tibbitt's thing, you can, but you don't really need to. Then it goes to a 150 kilohertz low pass filter, or you don't have to go through the low pass filter, you can go around it. For the HF path, you can go through a 15 megahertz filter, a 30 megahertz low pass filter, or you can bypass the filters. I like bypassing the filters. Whichever way you go into a 14-bit A to D, and the clock generator generates the clock to digitize the signal. Each time you digitize, the data goes into a memory. The memory is 256K deep. There's an address counter that chooses where each sample goes. So that's where your analog waveform goes when you capture it. So your N could be up to 256K samples. So here's a little background on it. It's a 14-bit, 65 megahertz ADC. 65 megahertz as fast as you can go. But remember, you can always do aliasing. You can always do subsampling or aliasing. 14-bit, 65 megahertz ADC, minus 80 dB THD at 1 megahertz, minus 70 dB THD at 10 megahertz. For the LF path, you can go up to 8 volts peak to peak, maximum input, single-ended or differential, notch and low-pass filters with post-filter gain or filter bypass. Or you can go through the HF path, which is 4 volts peak to peak max, and single-ended or differential, and then 15 megahertz or 30 megahertz low-pass filters or filter bypass. And so here's a picture of the ACI. Again, this was built by Applicos. You can see it says Applicos. So Applicos built those modules for Nextest. Okay, the clock generator. Now remember, I talk about coherent sampling all the time. The clock generator is crucial to that. So I'll go into a block diagram and show you all the details of the clock generator eventually. But here's the basics. High performance clock generator provides coherent clocks for mixed signal and digital based on a very low jitter 200 megahertz reference. Programmable PLL with auto-optimizing software. That was Daver. Period resolution of 3.44 picoseconds average. That's the kind of resolution we could get. With that kind of resolution, you don't actually have to be coherent. You can be really, really close. Low jitter performance, less than 10 picoseconds RMS. We had a customer, I showed him this, and we had a customer that said, that's not low jitter. We make a lower jitter PLL than that. Sorry, can't help you. Vector-triggered clocks allow true mixed signal testing. That's a big deal. That means that you can trigger the beginning of a waveform or trigger the beginning of a capture from the digital pattern. That was a really big deal. So you could tell it to start or stop a capture or start and stop a waveform from the digital pattern. because the digital pattern is running somewhere in the background. We're talking mixed signal devices. So there's digital going to the device and there's analog going to the device. So the AWI and the ACI can be triggered from the digital pattern. You can turn it on, you can turn it off, you can do it on, off, whatever you want to do. Okay, the analog instruments, we have a VI, that is voltage, current, force, and measure unit. That's a VI. 4 bias supplies, 2 device power supplies, a differential voltmeter. All instruments are referenced to analog ground, and all are 16-bit force and measure, 12-bit compare. What do you mean compare? That means on the Nextest, they generally did this, and so we incorporated it into the MSPC. You can just set a level where you want to compare. So let's say you want to set an IDD test, and you want to say, okay, I just want to know if the current exceeds 100 milliamps. So what you do is you set 100 milliamps in a limit register, and then from a vector trigger, you can say, okay, is it more than 100 milliamps? Yes or no? If it is, it flags a bit, and then you can fail it. So you don't actually have to measure anything. That means you can get through it fast. That's the trick. I mean, we're trying to test these parts as quickly as possible. Okay, these instruments are available through any pin in the DC matrix. So pins 49 to 64, those are available. All those instruments are available to any one of those pins. The bias supplies, there's 4 per MSPC board, 4 quadrant bias supplies, plus or minus 16 volts at up to 50 milliamps, and up to 200 milliamps available at plus 8 to minus 6. So if you only need to go up to 50 milliamps, you can go up to plus minus 16 volts. We had a lot of parts like that with the Vista. It was a problem because they couldn't get their bias supplies that high. But we learned a lot. When I worked at Credence, I learned a lot about what to do and what not to do. And so we incorporated that into the mixed signal pin card on the Nextest. Okay, 2 of the bias supplies are Kelvin sensed, 2 are internally sensed. 400 milliamp and 4 milliamp current ranges is 16 bits, which means 12.5 microamp resolution and 125 nanoamp resolution. And you could digitize the reading or do fast go, no-go testing. If you want to go for speed, don't measure anything, just do go, no-go. It was available through any pin on the matrix. And then the device power supplies. Remember, there's already device power supplies for the digital, but mixed signal parts generally have digital power supplies and analog power supplies. So the digital power supplies provide the digital for the digital pins and the digital parts of the device. The analog power supplies, like in a microcontroller with a DAC and an ADC. Microcontroller uses digital, but the microcontroller DAC uses an analog DPS. So that has to be separate. And that's because there's a separate ground. And you have to make sure, it's really crazy. You have to make sure that the grounds don't connect anywhere except exactly right under the device. We can force voltage up to 16 volts at 300 milliamps, and you can gang them to get up to 600 milliamps. So you can gang the 2 device power supplies. Measure ranges plus or minus 400 milliamps down to 4 microamps. Now, we did a special thing on the device power supplies. I did it. That made sure you could do IDQ. Even with those ranges, let's say you selected the 4 microamp range so that you could do IDQ. So you choose the 4 microamp range. But you can get up to the maximum current, 300 milliamps, out of a device power supply, even if it's in the 4 microamp range. That was something I insisted on, and Mike Furlan was able to do that for me. So a DPS, you could put it in the 4 microamp range or the 400 microamp range or whatever, and you can get the maximum current anytime. You could digitize readings or do fast go, no-go testing. It had a programmable slew rate. That's a big deal. Sometimes slew rate is a problem. There's a lot of times when a DPS, if it moves too fast, it makes things oscillate. So you can slow it down a little bit. The outputs go directly to the load board. Does not consume matrix pins. That's a nice thing about that. So all those pins, 512 pin GT, does not include the pins that have the DPSs on them. So all those DPSs go out there, they can be ganged together and they don't consume your 512 pins. Okay, also on the mixed signal pin card is something called the modulator. DPS and bias supplies can use the modulator. The modulator is a mini AWI, mini AWG. It has a 10-bit DAC, 4-volt maximum peak-to-peak output, less than 1 megahertz maximum clock rate, but it's fully coherent. It's fully coherent with the digital and everything else. 1K deep waveform memory. So you can do things like power supply ripple rejection test, ramps for ADCs, comparative threshold testing, all kinds of things. So that's actually an extra AWG. And then the differential voltmeter. So while the modulator acts like an extra AWG, the differential voltmeter can act like an extra ACI. Single-ended or differential voltmeter, 4 voltage ranges, plus minus 4 volts with 125 microvolt resolution, plus minus 2 volts with 62.5 microvolt resolution, plus minus 1 volt with 32 microvolt of resolution, plus minus 500 millivolts with 15.625 microvolts resolution, and then plus minus 10.5 volt common mode rejection in differential mode, available through any pin on the DC matrix, and you can use sample measurements up to 80 kilohertz. MSPC includes a removable NIST traceable standard, so you can have it calibrated by the NIST agent, and he'll verify that it's all calibrated. And now that means when you plug that in, your whole Maverick is calibrated. All instruments can be calibrated against the Cal standard. Requires no external instruments or fixtures. That's a really nice thing. And then finally, the digital capture instrument. Digital capture instrument is used to capture non-deterministic data from ADCs. Lightning leverages the Maverick's error catch RAM for DCI functions. Basically, Dava rewrote the error catch RAM to be a DCI. The DCI API set up the memory for coherent data capture on any digital pins. You can capture from 288 meg by 1 bit to 18 meg by 36 bits and capture it up to a 66 megahertz rate. So that was a DCI. It was on all the digital pins, but it was called error catch RAM. But Dava recoded everything so that it was called DCI, and it had specific routines for capturing digital data. So for ADCs and other things like that, you could capture digital data very deep, very, very deep, and up to 36 bits wide. So it's pretty cool. Now that is the beginning of the MSPC training course. So we already talked about DSP. Now the MSPC, mixed signal pin card, you can do all this stuff on the mixed signal pin card. So it's pretty cool. All right, I'm afraid it's going to rain, even though it's friggin' August. It should not rain in August, but hey, this is Oregon. So once again, from the river, this is Dan Bullard. See ya.